shown, and partially also at Eidgenössische Materialprüfanstalt, EMPA, in Switzerland. So in this talk, I will first give an introduction of optical tweezers, then how the force was measured in our case with optical tweezers, then forces acting on photothermal motors, the potential utilization of our motor system, and then the systems I used for investigation, then additional calibrations that are in our case necessary for hot particles, then how we measure the photothermic force and thermophoratic force, and also the measurement of the steam bubble propulsion force, and then a short outlook. So the reasons for choosing optical tweezers is because they are like a ideal measurement tool for forces. So we don't touch the particle, there's no wall to disturb the flow around the particle. One can do a remote observation. One has a really vast choice of measurement wavelengths. Theoretically, one could go from radio waves to extreme UV. There's a wide range of solvents possible. And virtually any small object can be trapped, and the measurement is fairly fast, in our case, 3 seconds. The drawback is that optical tweezers are rather weak. So the trapping within the optical tweezers is based on a gradient force, and the highest density of light is in our case in the trap center. And the particle must have a different refractive index than the medium. So yeah, the refractive index difference cannot be too strong, otherwise the scattering force can push the particle out of the trap center again. And the motion of the particle left, right, up, down refracts the light in a different way, so of the main axis, and that creates a momentum to re-establish the particle at the trap center, and the forces are in our case in the piconewton range. So here's a graph. So that if the particle moves, for example, to the left-hand side, then in this case more light is scattered off axis, and then we have a net force in the direction back to the trap center until the particle position is restored. And this also works in the 3-dimensional axis system, so we can have a particle position restoration in 3D, and we can also measure the particle position. So another advantage of the optical trap is that it behaves really like an ideal Hookean spring. So the stronger the displacement, the stronger is the restoration force, and yeah, it's in up to a certain degree linearly correlated. So F equals minus kx, with k being the spring constant and x being the displacement. And in our case, it is first very important to determine the spring constant of the optical trap, and it's usually done via Brownian motion reduction of the particle in the optical trap. So for a dielectric particle, one has only the gradient force acting on the particle, and that is easily measured. And so we measure the reduction of Brownian motion. So one can use, for example, a power spectrum where one measures at very high frequency, like 50 kilohertz, and the 3D position of the particle in X, Y, and Z axis. And then one can fit with Lorentzian the change in the power spectrum density function, which is practically the real component of a Fourier transform of the of like 150,000 measurements in 3 seconds, and then one gets such a curve, and here the corner frequency relates to the trap stiffness, or one simply determines the position probability histogram of the particle, and then relates that to pristine motion. For example, the histogram width decreases in most cases linearly with increasing optical trap laser power, and that can be related to the trap stiffness and different laser powers. So usually for optical trap with high trap stiffness and objective overfilling and high numerical aperture objective, one gets a linear relation of laser power to trap stiffness, except for really high laser powers where then the particle is expelled. So in case of photothermal micromotor and hot Brownian particle, we have additional forces. For example, a homogeneous particle that is absorbing the light, one determines not only the gradient force, but also the photophoretic force here in blue, which is pushing the particle out of the trap. And for a Janus particle, one has in addition the thermophoretic force and the photophoretic force. So we have additional forces, and we need to relate that to the motion of the particle in the trap. So the photophoretic force was coined in the 1910s in Europe, and this force relates from the inhomogeneous heating of light-absorbing particles, and it requires surrounding gas. And it was first reported in space because there are also a low amount of particles, and in the past was used to explain the direction of comet tails. And the motion is usually away from the light source, except we have self-lensing effects. So there's also negative photophoretic force reported, but usually one has a positive direction, so away from the light source. And thermophoretic force is similar. However, the motion of the particle is light flux direction independent. So, and previous works usually, and the vast majority of micromotor research, one simply relates the force that the micromotor performs simply to the viscosity, the radius of the particle, and the speed of the particle. And the temperature and local viscosity changes are usually neglected, which is a necessity, because the temperature measurements of local and very small micromotors is very difficult. And so when we started our work, there were only 3 particles dealing with hot Brownian motion of micromotors. One was a Brownian Carnot engine and optical tweezers, and 2 other papers relating the temperature of the micromotor with local viscosity changes. And so our work also uses a similar approach. And the viscosity temperature relation I had in most works to be neglected because the temperature was simply not known or were very imprecise. So when I started this work, I had a discussion with my supervisor, Professor He, and we tried to discuss how we can measure temperatures at the micro and nano scales to improve our work, and also improve our guidance of micromotors, and also have more precise force measurements. So in an advanced science article in 2016, we reported that photothermal temperature measurements, and the additional force measurements we published last year and beginning of this year. So, and for my setup, I use 200,000 measurements because I have a quadrupole diode, and I read out the signals with 50 kilohertz. And these 4-field diode signals are then converted into 3D positions. So I have 50 kilohertz sampling rate. And so we have here a laser beam, which is then expanded and guided via a high numerical aperture objective into our sample chamber. And then also we collect the scattered light, forward scattered light, and guide it to the quadrupole diode. And at the same time, we also perform a video recording of the particles. So, and HIT, we had in the past 20 times slower measurements, and there we had problems with our theory. So for the detailed force measurements, we were then rebuilding another setup in ETH with faster measurements. So, and for this calibration for hot particles, the Brownian motion of hot particles reduces the trap stiffness, and the thermal Brownian motion has no force vector. So it's not enough to simply measure the temperature, but also to calibrate the reduction in trapping stiffness by the non-directional thermal Brownian motion. And high temperature can lead to an overestimation of the driving force by up to factor 3 in our experiments. And therefore, we were first measuring the temperature, and we related the diffusion in the single dimensional cases for each diffusion dimension using this relation. And so here we have a measurement of high numerical aperture optical tweezers of a hot Brownian particle, and we still determine a linear decrease of the histogram width because the optical trapping force has to be stronger than the thermal Brownian motion. And in our case, yeah, we then were normalizing this optical trapping for histogram width for each laser power case, and for normalization we used a simple dielectric particle, and then we determined that there's an increase in relative diffusion between the hot Brownian particle and the dielectric particle, and this increase in diffusion for laser power can be related to increase in temperature of the particle. So we have a linear increase in temperature in this case, but it's different between Z dimension and X and Y dimension because the particle is anisotropically heating. So the Z dimension is the light flux direction of the laser. And therefore, of course, along the light flux direction, we have higher temperature increase. So yeah, our hot Brownian particles were evenly coated with gold nanoparticles, as you can see here, and also in the EDX. So this is SEM micrograph and SEM EDX. And the photophoretic forces along the Z-axis of the hot Brownian particle. And after thermal calibration and force calibration, we were able to determine a photophoretic force, which after some setup point is nearly linearly increasing with the laser power, which is expected when we increase the laser power linearly. And the force that we determined in our case is between 1 and 2 piconewton, which is comparable to E. coli bacteria. So in the next step, we were using a similar approach to measure Janus particles. So in our case, the particle is trapped always with the dielectric side in the optical tweezers. This is because our particles are larger than the wavelengths of light, and they are large enough to rotate. And in our case, the scattering of the gold nanoparticles, of the gold shell on the microparticle is rotating the gold out of the trap center, and therefore it's trapped with the dielectric side. And we can also rotate the microparticle with the laser polarization. And the gold shell is still touched at the border here by the light because we have a high numerical aperture, and it's heating significantly, and therefore the strongest force in this case is the photophoretic force, and the thermophoretic force is not as strong, which is understandable with the light flux direction. So in the next step, we try to change the numerical aperture of the laser because we were comparing different lensing effects and scattering effects. And another advantage is we try to reduce the heating on the gold shell of the Janus particle. so our main goal was to reduce the photophoretic component and increase the thermophoratic component. So we use now, instead of a 20% objective overfilling laser, a factor 4 underfilling laser. So instead of NA 0.95, we use now 0.24. And our optical trap is now 10 times weaker. And the local heating on the gold shell is would be up to 16 times higher. So we would be able to push it more, and that is then comparable with some systems utilized in other articles. And the position distribution of the particle for our laser changes. So instead of a very high numerical aperture, we have now a low numerical aperture with still a large scattering component. And so due to the stronger local heating and a local light flux, we have now overheating of water, and we create vapor bubbles. Surprisingly, with a lower probability at the lower side and a higher probability of the top side of the hot browning particle. This is because we have a self-lensing effect here due to the shape and the size of the particle. And so we were then only able to see the bubbles which then stepped over the border here. And so the microparticle was then really making fast up and down movement, as you can see here. And Z position histogram, it moved up and down due to the particles being very strong light absorbers, and therefore we had a lot of vapor bubbles at the top and the bottom of the particle, which they moved up, down. And the optical trap was strong enough to push the particle also back to the equilibrium position until then the next bubble started to emerge. And yeah, we then did again position calibration and temperature calibration, and then we fitted the photophoretic force here in the red line. And since the photophoretic force should continue linearly, we have here a linear extended fit here. And at the point when the gas bubble, the steam bubble starts, or when the water starts cooking around the particle, and the bubbles start to emerge, we have a deviation from the expected increase in photophoretic force. We have a much lower determined force. This is because the bubbles, the steam bubbles preferably nucleate at the top of the particle, and therefore they push the particle down. So we have here a negative force component from the cavitation force, which counteracts the photophoretic force. And we also saw that in our guiding principle of the micromotor, it was always in close to the focal plane of the microscope, so it didn't move up. And another advantage when the water is so hot around this particle is that we were able to guide it better than with high numerical aperture optical tweezers. So we had an easier to move particle despite the particle being so hot. So this is a surprisingly positive effect. So for the Johannes micromotor, we have here the same effect like before. So the particle was always trapped with the dielectric side in our optical tweezers, which is understandable because we still have the scattering component of the gold nano shell, and therefore it rotates out of the trap. And we additionally have a refraction of light and this direction of the shell, and therefore we have a stable nucleation point of the gas bubble. So the shell is very strongly light absorbing. And so here is the steam bubble, which grows and then is released. And we have, due to the stable nucleation side, a much more regular motion of the particle. And also in the position histogram, we have steam engine-like effect. So this is similar to the microscopic steam engine reported by other authors, but we were in this case using a Johannes particle. And here in this case as well, we have counteracting of the steam bubble against the photophoretic force due to the stronger light absorption of the gold Janus particles in this case compared to the hot brownian particles. The total force we determined is negative. Therefore, the particle was actually pushed down compared to the focal plane of the microscope. That's why the pictures are not that nice. And interestingly, due to the nucleation point of our steam bubbles, the steam bubble force and the thermophoratic component were summing up. Therefore, we had a advantage and an increase in the thermophoretic force direction. So it's the same force vector. So yeah, in result, the heating efficiency and the trapping probabilities depend strongly on the laser shape. The photophoretic force can be measured, and photophoretic and thermophoretic forces can be analyzed if the force vector dimension is in different direction on the three-dimensional coordinate system. The steam bubble propulsion force can be analyzed. Steam bubble propulsion force was in this case an opposite force vector to photophoretic and therefore position correcting. And also the local viscosity around the micromotors can be reduced if the micromotor is hot by factor 4, and if you work in a steam bubble environment up to 64. So the motors can be much faster when the viscosity is reduced. So in the future, we want to do more analysis of bubble propulsion and also measure if our motors are actually heated by our system in addition. And yeah, I also want to investigate further local viscosity changes and temperatures of various kind of micromotors. And yeah, I also want to use more on the self-focal plane correcting of micromotors to improve guidance and also visualization. And yeah, I also want to extend the approach for different kind of bubble propulsion and guiding principles. So with this, I would like to acknowledge National Natural Science Foundation of China, ETH, and HIT, which supported my work a lot. And I especially would like to thank Professor He, Professor Wang, and also the ETH Quantum Photonics and Optics group for discussion, which helped me a lot in the past. And with this, I would like to thank you for listening and yeah, ask if there are any questions.
Okay, thank you, Professor Johannes. So if there are any questions from audience, please feel free to ask your question.
So if not, maybe I can stop sharing.
Maybe we can wait a minute.